So when we draw cubic functions, when you graph them, look like this. Okay, this is what the cubic function looks like. So it's kind of linear-ish in that it is going out both directions like a line does, but there is a curve in the middle. This is what y equals x cubed looks like. Now, when I start adding in other numbers, like when I start adding in x squared and x and then constants and stuff, that's going to change it. So it may end up being like a little more curvy. Okay? But this is what the cubic parent function looks like. What can you tell me about this function just from looking at it? It what? It crosses the origin, so that means that it has an x-intercept at 0, 0. Okay. What else?
If you took a parabola and took one side.
Yeah, so if you took a parabola and took one side, you could flip it and you would end up with that. That is true. Anything else? It does have a nice curve to it.
What?
Would it be what? If you look at the right end of the graph, where's the right end pointing? So what does that tell us about our function? It's positive.
Does that mean that its domain and range are both like infinite?
Yes, it's exactly what this means, is that our domain and range for both of these are all real numbers, or negative infinity to positive infinity, however you want to write that. Our domain and range is all real numbers. So just like a line, it extends out both ways. You want me to blow your mind even more? Anything with an odd exponent, we'll do that. So what would it look like then if our a value of our graph was negative? What would happen to our graph? Yes, the right side would be down and the left side would be up. So it would look something like this. And you can always tell, by the way, if a function is positive or negative by looking at the right end of the graph. Wherever the right end of the graph is pointing always tells you whether the function is negative or positive. That's going to come in handy next week because I'm going to be giving you some information and you're going to have to graph the functions. So you need to understand what that means in order for it to be negative and positive. Okay. Do these have a vertex? They do not. What is a vertex?
It's the highest or lowest.
Okay. Highest or lowest point is the point where the graph curves at some point. So there's not one of those. There is what's called a point of inflection in this. And that's a whole way into calculus thing, so I'm not going to get into that. But there's a point of inflection because the concavity changes. Does it have an axis of symmetry? Is this graph symmetrical? Is there some way you could fold it and the two halves would be identical?
No.
Could you make two folds and the two halves be identical?
Yes.
How could you fold it?
Fold it in half, then you fold it down.
Yeah, you have to fold it like hamburger and hot dog style. If you did both, that would make it symmetric. It would be the same. That means when you can do that, when you can fold it two times like hamburger and hot dog style, that means that graph is symmetrical about the origin. That's what that translates into. Y'all learned about symmetry about the origin in geometry last year? Or you will learn about symmetry around the origin in geometry. Okay? When you learned about symmetry around the origin, that means if you fold it over the x-axis and fold it across the y-axis, and those two halves are on top of each other, they're symmetrical about the origin. So there is no axis of symmetry. Is there a maximum or minimum for this function?
No.
Nope. So we're going to have a lot of nones today. And that's okay because it's important to understand why these words don't have not nones in the habits, like black and white, but nones non-existent. It's important to understand why these parabola, or why this x cubed, this cubic function doesn't have these things. What about this negative function? What about my domain and range? What's that going to be? All real numbers. And when we say all real numbers, what we literally mean is that my graph continues to grow left and right, and my graph continues to grow up and down. It never stops going either direction. All right. Increasing and decreasing functions. Okay, let's start with increasing. What does it mean to be an increasing function? It's going up. And when we read it from left to right, it goes up. And then decreasing means that it's going down. So if I look at our function here, if I start from the left side and I follow the graph, which way am I going? Increasing. Am I always increasing? Okay, so this first function here, the positive function, is it ever a decreasing function? No. Oh, you can't read the blue on that. Okay, it is never a decreasing function. That says never, not hover.
But what about the one going down?
We'll get to that one. Is that better? Okay, never a decreasing function. And then how would we say that it's increasing from what to what? Negative infinity to positive infinity. Or we could also write what? All real numbers, the double R. So I'm going to write negative infinity to positive infinity just because I haven't written that today. And we do need to remember that that's the same thing as all real numbers. Is the same thing going to be true about our negative function? It's the opposite. So is it decreasing? So that means it's decreasing always, because if you start from the left side and follow the graph, you're always going down towards negative infinity. Yes, when you identify increasing and decreasing, you always start at the left side of the graph and move to the right side. So it's decreasing from negative infinity to positive infinity, and it's increasing never. And that one actually looks like never. So for every parent function, it's important that we have like just our standard table of values. This helps us kind of see what the graph looks like. The table of values for the parent function just means I plug in -6 for x into my function x cubed. So if I plug in -6 into x cubed, what is -6 cubed?
It's a negative whatever something times 36.
216. -6 to the third power is negative 216. What about -5 to the third power? What's -5 cubed? Negative 125. So all I'm doing here is I'm taking my function, y equals x cubed, and instead of x, I'm plugging in each of my numbers. All these numbers.
Is that 216?
Yes, that is negative 216. Okay, so what's going to happen if I plug in -4? What's -4 times -4 times -4? Negative 64. -4 times -4 times -4 is -64. Okay, what about -3 times -3 times -3? Okay, -2 times -2 times -2. And then -1 cubed? Okay. And then 0 cubed. Okay, what's going to happen on the other side? Yeah, it's just going to be positive. Same numbers, just different signs. I'm not even going to go through the math. So that'd be 1, 8, 27, 64, 125, and 216. So if I were to plot all those points, which we can't, obviously. I'm not going to make you plot the point 6, 216. But if I were to make you do that, you would get your cubic function. Okay, so now look at your book. Okay, so looking at the first page of 6.1, which is page 315, let's transfer over the table of values. They've given us some x's, not all the same x's, but just some of them. So when x is -2, y is what for our parent function? -8, and when x was -1, it was 1, and then 0, 1, and 8. And over here on the right, I want you to graph those points. So we're going to plot those points, -2, -8. I definitely graphed these wrong first period, as some child so kindly pointed out to me. So I'm going to plot my points just so I have my graph here. And then we're going to answer some questions about this graph, and we're going to learn a little bit of new vocabulary. All right, so we've already decided the domain and range. Domain they filled in for us, we said was all real numbers. What was our range of our parent function? All real numbers.
I didn't know that body parts were
So the next part is in behavior. Now, you told me just a second ago when I asked you, you said, what happens at the end? I'm going to give you a very, just broken down definition of this to help you understand it and just to be a little more specific than that. It's what, no, hold on, sorry, where, that's the word I'm looking for, is the graph going at the left and on the left and right sides. That's what in behavior is. Where is the graph going on the left and right ends? That's what in behavior is. Where is the graph going on the left and right ends? So the way that we write in behavior, this is going to appear new. So it says as x, and then there's an arrow. When we see that arrow in math, it means approaches. So as x approaches or as x goes to, either one. As x approaches positive infinity. So think about as my x's, which go left and right. Which way is positive infinity?
Right.
To the right. If my x is my left and right, positive infinity is out to the right. So when it's saying as x approaches positive infinity, it's asking what's happening to the right side of my graph. It's asking what's happening as I go out to the right. So going back and looking at my graph here, as I follow my graph to the right, which way are my y's going? Up to positive or negative infinity? So that's what I would write here, f of x, because f of x is the same thing as y. We're saying that my y's go to or my y's approach positive infinity. So as my x's go out to the right, my y's are going up. So then what do you think the second one means? As x approaches negative infinity, which side of the graph are we looking at there? The left side. So looking at my graph, as I go to the left, which way is my graph going? It's going towards negative infinity. So my end behavior is that f of x, or my y's, go towards negative infinity. Okay. The next thing that's on there, zeros of the function. What are zeros also known as? X-intercepts. And there's an x-intercept at x equals 0. And Joe, I believe you said that earlier today. You told me there was an x-intercept there. But it's important to note that zeros are the same as x-intercepts. You have to know that. That's so critical. Because those points actually have multiple names. They're called root solution zeros, x-intercepts. You'll hear them called critical points, points of inflection. Like they have all these different names that you're going to learn. But the common one throughout every class you take is zeros. Okay? Sometimes you'll hear me call them roots. This is just kind of like a public service announcement for you. You'll hear me call them roots because for a long time, that was the most common term. And now they've kind of in the last couple of years switched over to zeros. But since I've been teaching for so long, I sometimes default back to the old ways. So if you ever hear me say roots, know that I'm talking about zeros and x-intercepts because they're the same thing. So the next question asks you where the function has positive values. When it asks where the function has positive values, that is wanting to know where are the y's positive? Where are my y's greater than 0? That's what it's asking. So think about on a graph with an x and a y axis. If your y's are greater than 0, where are you at? I'm above the x-axis. So if it's asking me where the function is positive, it's asking me where is the graph above the x-axis. That's what it's wanting to know. It's asking me where the graph is above the x-axis. If I look at my graph, this is the piece above the x-axis. So all of those y's are positive. What can you tell me about all those x's? They're also positive. And we know they're positive because this entire graph is to the right of the y-axis. So that's what they mean here when they say that my x's are greater than 0. They're saying that all of my x's are positive. So what about, the next question says where the function has negative values. So if it has negative values, I'm not looking at what's above the x-axis. What am I looking at? Below the x-axis. So looking at my graph again, If I want to know what part of it is below the x-axis, well, that's this piece, because there's the x-axis cut off at the top. What can you tell me about my x values here? They're all negative. So that would mean my function has negative values when my x's are less than 0. The next part where the function is increasing, you already told me that. We already filled that out. Where was it increasing? Where is it increasing? Increasing. Look back at your reference page. You already filled out. Negative infinity to positive infinity. It is always increasing. Increasing means as I read it from left to right, which way am I going? I'm going up the whole time. Okay, this last part. It asks you about even and odd functions. For today, because this is a very generic definition of this, even and odd functions are somewhat based on the exponent. There's a little more to it than that, but the exponent is a good indicator of whether a function is even or odd. So what's our exponent of our problem? Cubed. Is that an even or an odd number?
Odd.
So this is an odd function. Now again, there's a little more that goes into even and odd functions than that, but that's kind of the foundation of what it means to be even and odd. So that means that y equals x squared would be what type of function?
Even.
Even. Again, it gets a little more complicated, but that's kind of the basics, so that's where we're going to start at least for today. What's the important thing to remember about b?
You have to use the
You have to flip it. You're using the reciprocal or the refliprical. Okay? So b is the refliprical. It's always the opposite. Okay, what about c? What does that do? Moves it left or right, but it's always the opposite. Okay. So we're going to apply that information to some problems. Starting with problem A on page 316. And again, the good thing is we've already learned all of this. So we're taking that same knowledge we had from absolute value functions and applying it to our cubic functions. So it says the graph of g of x equals x minus 2 cubed. So what is this minus 2 going to do to the graph?
Move it to the right 2.
It's going to move it right 2 units. How can you tell if it's a shift versus a stretch or compression? Yes, that's exactly what it is. If it's being subtracted or added, it's going to be shifting it. If you're multiplying, that's when it stretches and compresses things. The same thing was true in geometry, that when you dilated things, the reason you dilated them was because you multiplied by something. Okay, what about the next one? F of x or g of x equals x plus 2 cubed. So what's that plus 2 going to do? It's going to move it left 2 units. Okay. What about x cubed plus 2, the next one? What's that plus 2 going to do? Up 2. And then x cubed minus 2, what's that going to do? Okay. All right. Now I'm getting into 2x to the third here. What is that 2? Bless you. Bless you. What is that 2 going to do? Vertical compression or vertical stretch? It's going to be a vertical stretch. Outside is normal. If I multiply by 2, the number I'm multiplying gets bigger. So it's a vertical stretch by a factor of 2. Okay. What about the negative 1/2?
That would be it, and then it's going to compress it.
What part tells us that it flips? The negative piece. Anytime I have negatives, there's some sort of reflection that occurs. So if that's negative, then it's a vertical reflection. So I'm reflecting over which axis? The x-axis. So it's going to reflect over the x-axis. And what's the 1/2 going to do? Compress it. So it's a vertical compression of 1/2 as well as a reflection across the x-axis. And again, all of this information is on your reference page. I thought, you know what, there's no reason for us to go and write it all in. I was just going to give you mine that I already had filled out. Thought that would be a good place to start for this one. So, did I spell reflect right? Yeah, it just looks weird. All right. Next page. Problem A, or D, I'm sorry. All right, what about this 1/2 x all to the third power? What is this? It is a horizontal stretch of, what's my scale factor here? 2. What do you have to do with horizontal stretches and compressions? You have to flip the fraction. So it's a horizontal stretch of 2. And remember, horizontal stretches and compressions are always the opposite of what you think it should be. Because 1/2 you're thinking, oh, that should make it smaller. It doesn't. 1/2 is actually going to make it bigger horizontally. What about part B? The graph of g of x equals 2x all to the third power. What's this 2 going to do?
Horizontal compression.
It's a horizontal compression of 1/2. Again, I have to take the reciprocal. The reciprocal is also known as the reciprocal. Thank you, Mr. Riley. Do what?
The reflection is over the x-axis.
So, okay, if we look at C, is that what you're talking about, is C?
Yeah.
Okay.
The one we just did.
All right, the one we just did was over the x-axis because where was that negative sign?
Before.
It was before. Where is this negative sign? Inside the parentheses. So this negative sign tells us that it's going to do what?
Reflect over the y-axis.
It's reflect over the y-axis this time. So it's going to flip over the y. Okay? And then what about the 1/2? What is that 1/2 going to do? A horizontal stretch of 2. And you're welcome to write HS and HC and VS and VC. I'm fine with that. You can also take the time and write all the words. Okay? Either one is fine with me. I'm not really particular on that as long as you know what it is that you are doing. All right, I'm going to assign your homework part of it. The first part of your homework, the part that I'm giving you tonight, is 2 through 15. And on 2 through 15, all of them, all I want you to do is describe the transformations. That is not going to change on these problems. I'm not going to ask you to do anything else on these problems. Tomorrow, I'm going to give you like 7 more problems to do. Okay? But for 2 through 15, on all of those, your instructions are to describe the transformation despite what the instructions may say in the book. Okay? Some of them ask you to do a little bit more, but 2 through 15, all I want you to do is describe those transformations.